All right. How's everyone feeling? Any questions before we get started? Serious or otherwise? All right. Well, if you have any thoughts at all, do interrupt me. Today, we're going to continue looking at forces and their laws. We're going to start with a little bit of practice of what we've already done, and then we're going to look at even more new types of force. It's Friday though, so my goal is for us to be able to head on to our weekend soon. To start with a little bit of practice, in reference to things from both Monday and Wednesday, we are going to examine all the forces currently acting on a 10-kilogram box, given that it is being pushed horizontally along a flat, level surface on planet Earth, and a 200 Newton force pointing west or right, and a 250 Newton force pointing east or, hey, what? 200 Newton force pointing west or left, and 250 Newton force pointing east or right. First thing I'd like you guys to do is draw me a free body diagram showing all of the forces currently acting on this box, and then try to figure out what they all are, what they're equal to, and how they add up to the net force on this box. I'm going to give you guys a couple of minutes to ponder that and get your drawings and work together, and I'm going to drink some water because I already can't talk. All right. What sort of conclusions have you drawn? Namely, to start with, how many forces are currently acting on this box? Two are listed, but if we look at the required forces for this thing to be sliding across the ground, flat ground on planet Earth, there would actually need to be a total of 4. We're told about the 200 pointing this way and the 250 pointing this way. What are the other two that would need to be here? Gravity and normal force, very good. If you're on planet Earth, you really can't escape these two. And at a cursory glance, what would the relationship between gravity and normal force be if this box is being pushed to either side only? Vertically speaking, a net force of 0. So whatever these two things are, they're likely canceling out so that the box does not accelerate up or down, only accelerating side to side. Does that sound consistent with what you guys are thinking? All right, very good. Given all of that, what would the net force on this box logically be if it is sliding across the ground? 0 is technically correct, but only in one axis. So if we look at the vertical forces that are present, they would have to cancel out to keep the box from accelerating up or down. But what about horizontally? Very good. They would add up to 50 because they oppose each other. So the net force is 50 newtons to the right and nothing vertically. Questions so far? All right. What is the value of every force on your free body diagram? Two of them already have numbers. How would you find numbers for the other two? All right. By definition, Fg equals m times g, so 10 times negative 9.8 should give us 98 newtons down for gravity. And according to this previous statement, where normal force and gravity must add up to 0 to keep the box on the ground, normal force must therefore be positive 98. Yes?
Would you have to put the negative if it's already coming down?
I like to try to be as consistent as possible because you're correct. The arrow does technically take care of the negative, but I find that when I'm doing work on the board, if I just write 98 and then later on if I take that number and put it into a formula and I have to then make it negative, that sometimes trips a few of my students up when I have to explain that extra step. So I try to keep it negative for the internal consistency. It's a good question though, you are correct. The arrow technically takes care of it. I suppose then technically this 200 should also be negative. Last step, if the box's mass is 10 kilograms, what will the acceleration of this box be?
5 seconds squared.
Very good. And we get that number by using Newton's second law. We've determined the net force is 50 newtons to the right. So 50 pointing to the right is going to equal 10 times A. Therefore, A should equal 5 meters per second squared, specifically pointing to the right. Because whatever the direction of net force is, the direction of the net acceleration will match, because they are the only two vectors present in this formula. One inherits its direction from the other. In the case where an object is falling down, it is accelerating down because the net force from gravity points down. In the case of, say, the Hulk jumping in front of a train, the train is slowing down, therefore accelerating backwards because the Hulk is pushing it backwards. Questions, comments, concerns? Feel all right with this one? All right. So, my goal with this one was just to compile together some of the various points from the last couple of days. Next thing we're going to be doing is we're going to continue looking at more new types of force and how they then interact with the laws of motion. So these next two forces we're going to cover because they will pop up starting in lab next week. Tension definitely will. There's probably friction will probably happen for the lab the week after, but the main thing I want to focus on right now is tension. Again, lab next week will focus on it. So if we don't get to friction, I don't really think we're going to fully describe friction today, so we'll come back to this one later. Right now we're going to focus on tension. And that's another one of those physics words that people tend to hear a lot, but may not have formally defined it in words. So the first thing I'm going to do is define how physicists look at tension. The definition of tension is it is a response to when you take an object and pull it outwards on either side of it. The most simplest definition of tension that I could give is that it's the force that ropes exert. Ropes exert tension, and other rope-like things as well, including you know, cables and bungee cords and also springs. And the way that tension works is it is very specifically a response to when the object is being pulled on outwards on both sides. If I just hold this spring in my hands, is it currently under any tension? If I'm holding it like this, specifically. No, it's not under tension, and it's not currently exerting any tension, because I'm not currently pulling on either end. There are forces on it, gravity up and normal force from, I said that backwards, gravity down, normal force from my hand up, but those forces are not pulling outward on either of its sides. So the spring, is not currently under any tension. The spring only creates a tension response when I take the two ends of it and pull actively outwards on either end. So now this spring is under tension, and as a result, it will create a tension response to the outward pointing forces that I exert. When a spring or a rope or whatever tensile object you have is exerting tension, it very specifically exerts that force inward on both of its ends as a response to me pulling outward on both of its ends. To try to represent that with a picture, I'm going to erase the work we just did. And draw in a very poor representation of a rope. This box is a rope. I have decreed it as such. And in order for this rope to be under tension, I have to very specifically be pulling outward on either end. Specifically on both ends, actually, not just one, but both. Specifically, you do have to pull outward as a prerequisite for tension, because ropes don't tend to serve very well under compression if I'm pushing inward on both sides. So tension happens outward. Ropes are great at that, but push inwards and the whole thing kind of stops working. Pushing inward is called compression. There are objects that are great at that, but not ropes. So, you pull outward on either end of this thing. It is going to cause a Newton's third law action-reaction response. As a response to me pulling leftward on this side, the rope is going to pull rightward on my hand at this spot right here. But that's only on this side of the rope, because on the other side of the rope, something else, my other hand, is exerting a rightward pointing force. And as a response, the other end of the rope will pull in the opposite direction. So on either end of its own length, it's pulling in two different directions simultaneously. This is the conundrum of ropes. Anything that's under tension, anything that is exerting tension, always pulls inward on both ends, thereby meaning it's pulling in opposite directions simultaneously on both ends. Excuse me. Any object under tension or exerting tension is doing this, and just for some additional context, the common shorthands for tension that you will see on formula sheets and things like that, I'd be tempted to call it F subscript T, but some places just call it capital T. This is specifically capital English T, though. There's a few other places on your formula sheet that use Greek letter capital tau, not the same thing. But those won't come up for a while. The weird thing about ropes is they pull inward on both sides, technically into different directions. I bet you've noticed this before, even if you've never described it like this or thought of it consciously. And another example I'm going to try to give real quick is insert action movie of choice where someone's going to swing from a rope. In this particular case, if we kind of pause time at the lowest point of this swing, what's happening here is action protagonist number A here. They're pulling down on this end of the rope, their weight is being applied to this end of it, and as a response, the rope is going to pull up on them. And the rope has to be pulling up or else they would fall. So we know for a fact that on this end, the rope pulls upwards. But something different happens on the other end. On the other end, whatever the rope is tied to has to be pulling up on it, and as a response, the rope is pulling down at that point. It's pulling down on where it connects to the ceiling. Where this might come up in the movie is if the rope is tied to something that cannot stand that amount of force. The rope is going to pull down on the ceiling, and perhaps what the ceiling is made of can't stand that amount of force. For example, you wouldn't want to try to swing from a rope attached to these ceiling tiles, because these ceiling tiles cannot withstand human being levels of weight. So if I just literally stuck a rope in the middle of these things and tried to George of the Jungle off of it, things would go very badly for me. In order to do this successfully, you have to mount it in such a way that whatever it's tied to can withstand the force that the rope is pulling down at this spot. And likewise, the rope also has to be able to withstand all the forces that are currently acting on it. All different ropes, all made of different materials, can withstand different levels of tension before they just straight up snap, and then bad things happen. All of this anecdote is just to, again, point out the rope pulls inward on both sides. It's the same number on both sides, but it's two different directions on either side. How's that feel? Yes?
Would that be considered normal force where the ceiling is pointing up?
It could. It could, because the ceiling could only pull in perpendicular to itself as the rope is pulling perpendicularly outward. So, yes, actually. Yes, it could. Normally, we tend, within this particular class, we tend to only think about normal force coming out of something, but it can point in as long as it's still perpendicular to the surface. So, excellent observation. Yeah, that the ceiling there would be exerting a normal force. I've been doing this for decades and I haven't even connected that yet. Any other questions, thoughts, concerns? Okay. Let's get in a little bit of practice applying some of this information. This table question might be a bit of a doozy. That's why I'm doing it in class with you guys, and I anticipate us needing to cut it off at a certain point and then resume it on Monday. That's okay, that's intentional. So if the math starts feeling overwhelming, again, this one's meant, we're gonna do this one over the span of 2 days, it's fine. So let us examine the tension in a situation where you might find it. Here we have a series of ropes that are designed to hold that particular box in place. One of the applications of tension, if you were, say, to become an engineer of some description, is in designing systems that will move things around or possibly hold them in place. This is something that you might see in, say, a shipping yard using cranes to move things around, or even in show business, honestly, because stages and set designs still use ropes and pulley systems to move things around the set and, raise the curtain up and down. So there are people who are paid to design systems like this, and to do this successfully, say if you're hanging this 100 kilogram box from this system, you would need to make sure that all of your individual ropes can withstand the requisite amount of tension in this system. When you connect all these ropes like this, there's going to be tension in all of them. All three of the ropes pictured here will have tension in them. And what we are going to do is calculate the tension in each of these ropes required to hold this box up, so that we can, again, if you were an engineer building this system, you need to calculate the required tensions ahead of time and make sure that all of the ropes you're using can withstand that level of tension. Because this is a 100 kilogram box, which again is about the mass of a human like me, and you use just like string, that's not gonna go well. You want to use, cable or industrial rope that can withstand the correct amount of tension. So we have to predict how much tension is going to be there before we build the thing. So that is where someone might do this sort of math. And our job here is going to be, again, finding the tension in each rope. So I have begun by labeling the tension in each rope. There are 3 ropes here, and I've labeled them 1, 2, and 3 accordingly. Rope 1, 2, and 3, which likewise all contain tension 1, 2, and 3. And when examining tension, I find it useful to draw on your picture what direction that tension is acting at every single end of each rope. You've got 3 ropes here, and that means that each tension is going to act in 2 different directions on each end. So as a result, there are currently 6 arrows that I've drawn in. I'm going to actually kind of start with the 3rd one and then work our way back up. This 3rd rope, labeled tension 3, is the one that is most directly supporting the payload. This rope has to be pulling up on its lower end in order to actually be holding up the box. And if it's pulling up on this side, it must be pulling down on the other by virtue of the definition of tension. And the fact that it's pulling down on this end is what sends the rest of the ropes into a tensile state. And the other 2 ropes have to be pulling at least partially upwards to counteract that. So, where the other 2 ropes connect at this knot here, T2 is going to pull up and to the left along its length, which likewise means where it connects to the ceiling is going to pull down and to the right. Meanwhile, T1 is going to pull along its length up and rightward at this point, and therefore it'll pull down and leftward where it connects to the ceiling. So this map is just meant to demonstrate how the tension travels through the entire system. I kind of like how it shows the force traveling from the box all the way up into the ceiling. And as an added weak point, you want to check how much force was going into the ceiling to make sure that your connections there can withstand that amount of force. And I'm going to demonstrate to you how we calculate all those tensions. Any questions so far? Okay. So we have T1, T2, and T3 that we are after. And I'm going to recommend we start by going after T3. In tension situations like this, the usual strategy that I recommend is to begin by picking a knot, basically, a point where the ropes converge, and examining how all the forces interact at those particular spots. If we were to begin with this knot here, we would notice that all 3 tensions are acting together on that particular spot. So I will write out the net force acting on that spot would be the sum of all 3 of them. And if our goal is to have this whole system remain stationary, if you just want to hold that box in the air, what would the value of this net force be? 0. All these things need to add up to 0 if the goal is to hold it in place. Make sense? So at that spot, they're all gonna add up to 0. But since there's 3 of them, and we don't really have any numbers for them yet, we're not really gonna get any more information out of that knot at this time. So I'm going to recommend we now also begin examining this second knot down here. And just analyzing it in a very similar way. Net force at this position, likewise, we also want that to be 0, because otherwise the box wouldn't be stationary. So whatever forces are present at that second orange X need to add up to 0. What forces are acting at that spot?
Gravity, tension, pulling.
All right. We've got the tension in the third row pulling up, and the weight of the box pulling down. And we actually have enough information to kind of solve this side for T3, because we know the mass of the box, and that means we can find the weight of the box. How would we find the weight of a box? Force of gravity. And what is the formula for that? Yep, mass of the box times 9.8. So after factoring that in, T3 is our only unknown. And overall, this is going to tell us that the tension in rope 3 will be equal and opposite to the weight of the box at that particular point. Does that track so far? Okay. So at that point, T3 will equal positive 980. And that's already one of the 3 ropes completely solved. Questions, concerns? Yes.
So it's also pulling 90 newtons down from the knot.
Correct. That's why I wanted to put these arrows on here to start with. At this spot, T3 points up with 980 newtons. But at the exact same time, it's going to pull down on this spot with 980 newtons. It's the same number on both ends, just different directions. And that is going to help us figure out what's going on at this knot instead. Does that answer the question? Or, yeah. Any other questions before we continue on? Okay. So we now have a number for T3, which is great, but that would still leave 2 unknowns in here. Furthermore, if we had a number for T1 or T2, could we use this formula to figure out the rest of them as it's currently written? Tragically, we could not. The reason for that being, all 3 of these ropes are in different axes. So they would not all just add up normally. We would have to add up only the X's and only the Y's. And that means it's tray time. The 2 tensions that point at odd angles could be divvied up into their components. Now, we don't actually have numbers for T1 or T2 yet, but this is still an important step because only, for example, do the X components of the 2 separate tensions actually interact with each other. So before we proceed, we have to figure out how much of our unknown tensions are currently being divvied up between the two axes. And then we can use that information to rewrite this equation to be separately one for the x and one for the y. Any issues with how I have drawn the legs into this into these triangles?
Can you write in the green? The orange is kind of hard to see.
Oh, yes.
Thank you. Sorry for being picky.
No, you guys need to be able to see what is on the board. I'm up here, so I have an easier time physically reading it. Is that better?
Yes. Thank you.
I need to go raid the supply closet for more markers. When I'm thinking about it, does everyone understand how the same angles that are up here also end up down here? Okay. So if they're 30 degrees from the horizontal axis up here, they're still 30 degrees and 40 degrees from the horizontal axis down there. With those legs drawn in, I'm going to recommend we now use trig to divvy up our unknown hypotenuse into many different unknown leg components. Starting with T1, if this is our known 30-degree angle, which of the two legs would be opposite? Say it again. Ty. And that would leave x as the adjacent. So, SOHCAHTOA, sine opposite hypotenuse. Sine of the known 30 degrees would be the opposite y leg over the unknown hypotenuse. Likewise, cosine would be the unknown x leg under the unknown hypotenuse. Now again, we still don't have a value for T1 or T2, so we're not going to get numbers for the legs. Our goal is to just try to divide up the unknown hypotenuse into its two components so that we can actually proceed with net force calculations within the two separate axes. And so this would tell us that T1y is the unknown T1 times sine of 30, and T1x would be the unknown T1 times the cosine of 30. So our unknown legs are still in terms of the number that we want. And frankly, sine 30 and cosine 30 are just numbers. You could put them in your calculator and get just a number for it if you wanted to. Like, that's a known. It's not another thing we have to solve for. I'm just leaving it in this form because if I solve for a number, it's going to be a weird decimal value. Any questions arriving at this point? We're going to want to do exactly the same thing to the other side, to the other tension vector, so that we can similarly get the components and then work within one axis at a time. So the orientation is mirrored, so conveniently y would still be sine and x would still be cosine. So this would say sine of 45 equals T2y over T2. Therefore, T2y is unknown T2 times sine of 45 degrees. Meanwhile, cosine 45 would be T2x over T2, therefore unknown T2x is unknown T2 times, I almost wrote sine again, cosine of 45. That said, whatever number T2 is, the two legs of T2 would be the same, because that's how 45-degree triangles work. 45-degree right angles, rather. So all we've done is take each separate tension vector, divide it up into unknown components so that we can then work within just one axis at a time. Excuse me. Pardon. Questions so far? All right. So I'm going to take this thing and break it down into one separately for the x and one separately for the y. So net force in the x is still going to be 0, because we want all the net forces in either axis to be 0 for this thing to remain stationary. And what x forces are present at this particular knot? Yep, just the x components of the two angle tensions. Note that the way it's drawn, T3 does not have an x component, or rather, its x component would be 0 if we bothered to write it out. So, if I was being thorough, I would write T1x plus T2x plus T3x equals 0. But the second I start filling in numbers, that would become, for T1x, that would be, oh, I already wrote the 0. 0 equals, T1x is T1 sine of, nope, cosine. T1 cosine of 30. Then T2x is T2 cosine of 45. And T3x is 0. So it's just not contributing in the x-axis. All that's happening in the x-axis is the two components are opposing each other and canceling out. One last question about this before continuing on. What does the drawing tell us about the relationship between these two things?
They cancel each other out.
They cancel out, and that means that they must be equal and opposite. And the picture demonstrates that they should be pointing in opposite directions, meaning that we're going to have to manually add a negative sign onto one of them for the rest of the work to make any sense. The picture tells us T2x points in the traditionally negative axis. Your calculator trig wouldn't necessarily know that, so we have to add that negative in ourselves. They oppose each other, one of them has to be negative. And if you do that, that's conveniently going to make the next step make a lot more sense. If I actually take the -1 and send it over to the other side, that would definitively tell us that the two x legs are equal and opposite. And that's, frustratingly, all this one will tell us at this particular moment in time, because there's still two unknowns in it, those two tensions. So this one equation is not going to go anywhere else yet. Any questions arriving at that particular point, though? All it's saying is the two x components cancel out, which is what you want if you want this system to remain in place. Okay. So that's as far as our x-axis analysis is going to go right now. So now we're also going to look at the y-axis instead, or in addition, rather. So instead of the lump sums or the x legs, we'll now look at the y legs. So t1y plus t2y plus t3y equals 0. t1y is t1 sine of 30. t2y is t2 sine of 45. And t3y is the full 980 of t3, because t3 has no x component, it's just pulling down at that spot. Now, jumping off from what I just said, and in reference to something that someone said earlier, all tensions pull in opposite directions on either side. Just because T3 is positive 980 down here does not mean that it's positive 980 here. In fact, the image is telling us that the rope has to be pulling down at this spot. Meanwhile, the two other ropes are pulling vertically upwards at that spot. So even though it was 980 earlier, we've switched perspectives. We're on the other end of the rope now, meaning that T3Y points down from our current reference frame. So we have to add that negative manually in order for our math to work. Excuse me. Questions so far? Alright. Now, similar to the x-axis, we have the same two unknowns in here, meaning this one equation by itself also won't tell us anything, because there's still two things in it we don't know. There's still the same unknown T1, the same unknown T2. We can move the 980 to the other side, but that's not inherently going to give us a number for either single variable. And so by themselves, this is where the situation may just stop working. But what could we do instead, rather than just give up? I think so. I hear someone muttering it.
Can't you plug in T2 sine 45 from T1 sine 30?
Yep.
And then move the 980 over and just cancel everything out, basically divide.
You're getting to the right point. We have two equations with the same two unknown things in them. This has T1 and T2, and the only unknowns here are T1 and T2, and likewise the only unknowns here are T1 and T2. So we've created a scenario called, or at least that I call, two equations, two unknowns. Meaning we can use one to help find the other. If you've been working on the homework, it's the same as in the tortoise and the hare question. And I think we might have enough time to try to wrap this one up quickly, actually. So what I'm going to recommend we do is take this equation and just solve it, like rearrange it for either T1 or T2 very quickly. So I'm going to do, I'm just going to erase this whole thing. T1 equals T2 cos of 45 over cosine of 30. And that means that wherever you see a T1, you can write this instead. And that includes in the other axis equation. So, I'm going to take that second equation and rewrite it, but using this instead of T1. So same equation, but instead of T1, I'll write it with the T1 in there to start with. T1 sine of 30 plus T2 sine of 45. I'll go ahead and move the 980 over. So same equation as the whole y-axis one we just wrote, but now instead of T1, I'm going to write this instead. T2 cosine of 45 over cosine of 30. And it may look a little bit ugly, but now T2 is the only unknown left. Which means we can find a number for it. I'm going to recommend first of all, any questions? Feel okay so far? Familiar, I hope? Yes?
How'd you turn T1 to T2 cosine reverse?
Starting here, T1 cosine 30 equals T2 cosine 45. If you take this and just divide both sides by cosine of 30, that's going to cancel the cos 30 over here and put it into the denominator over here, which will turn this equation into this. T1 equals T2 times this fraction. So basically I just rearranged one of the equations into a form that I could use to plug into the other one.
But wouldn't your T1 and T2 have to be negative because they're equal numbers?
We already declared one of these legs to be negative, and that means when we added it to the other side, that gives us positive on both sides. Good observation. We've taken steps to account for that. On this new left side, there's a T2 multiplied into both terms, which means we can use the distributive property to pull that T2 out. And that would leave us with cosine 45 over cosine 30 times sine of 30 plus sine of 45 equals 980. Which looks ugly, but this can be solved for just a number. We know everything inside of this big parentheses now. Does anyone have any questions with how I jumped from here to here? Just distributing the T2 out and leaving behind all the trig that it was attached to. Cos 45 divided by cosine of 30 times the sine of 30 plus the sine of 45 compresses down into 1.115. Does anyone disagree? And that's equal to 980. Therefore, T2 should equal 980 divided by 1.115. And that tells us the tension in the second rope should be approximately 878 rounding newtons, which is slightly less than that of the first rope, but still most of that tension. And now that we have that number, we can take it and just put it back into our first equation to solve for T1. Two equations, two unknowns method can get kind of algebra-y at times, but by the end of things, it does work out nicely. So let's take that same answer times cos 45 divided by cosine of 30. And that tells us that T1 should in turn be about 718 newtons. So the single rope with the most tension in it is the third one, the first one we looked at. And that means you'd want to make sure to buy a rope that can handle more than 980 newtons of force. How do you feel? All right. It's Friday and that was a lot of math, so go take a break. Go have a weekend. Let me know if you have any questions. I do recommend continuing to look over the homework. Let me know if you guys need anything, and have a great weekend.